All right, guys.
I'm gonna go look hard, honestly. I'm like, what the heck is this?
Have you guys ever seen when they take two soda bottles and they connect them together
Yes.
and they make tornadoes in a bottle? You guys ever seen this before?
Yeah. I can never get the tornado.
You could never get what?
The tornado.
Oh.
I'm not shaking it.
Apparently we are done. Let's play it on a loop. Okay. So this idea right here is what our activity for the next several days is based on. So I want you to take just a moment as you are watching these water tornadoes, and at the top of page 22, you have a really poorly drawn representation of this. That's what this is like. It's these two different prisms connected in the middle because my art skills with drawing 2-liter pop bottles, just not so much. So forgive my bad art skills. And I want you to write down anything that you know or any kind of assumptions that you can make about this situation. What do you know about these two soda bottles? What do you know about the liquid inside them? Does it stay put? Does it move? What happens? Is it going out of one and into the other? If so, which one is it moving out of? Which one is it going into? If it's going out of one, what would that tell you about the rate of the one that it goes into? Does the amount of water total in this system change or stay the same? I want you to write down any initial thoughts you have about this water tornado here, okay? I'm going to give you guys about 2-3 minutes-ish. Jot down anything that you can think of about this situation. Pull out your book for me, dear. Page 22. Check your name up for me, hon. Pass it on. You didn't get a book yesterday? I'm not quite sure how that happened, but we will fix it now. All right. You're welcome. Take about 30 more seconds. I just want to make sure that we fully understand the situation before we get into trying to use this information at all. Because if you don't understand the situation, me asking you to do stuff with it, you're like, I don't know what's going on. I got nothing. What's happening between the top and the bottom? Talk to me about other things that we've mentioned in this unit up to this point. Rates, starting amounts, ending amounts. Thank you. I think we missed this row here. All right. Tell me any thoughts you guys had. What do we come up with? Come on. Seriously. What do we got? Yes, ma'am.
The speed of the bottles are different. Most of them go fast, the others are more slow.
Like the 3 different bottles? Okay. If I'm focused on just, and I love that you mentioned that, yeah. What do you think affects that rate? Yeah, I mean, honestly, this is like going a little bit outside of my area of expertise as far as what would affect that flow rate. Yes, sir. Oh, I thought you had a comment. If I was just looking at one of those bottles, is the bottle, like, is the liquid moving between the 2 sides?
No.
Where does the liquid start at?
Top.
All the liquid starts at the top. What happens to it as that tornado goes?
It goes down.
It goes down, so liquid drains out of the top. Total amount stays the same. I love that. Give me just a second. I'll get that written down because that's super important. Liquid leaves the top. Liquid enters the bottom. Total amount of liquid stays the same. Why does the total amount of liquid stay the same?
Because there's no openings for it to escape.
Yeah, there's no openings for it to escape from. It goes from one container into another container, and then after it's all gone through, you can turn it over and do it again. As long as it doesn't spring a leak somewhere, you can keep doing this over and over and over, right? So however much we start with at the top, when it's all done running, that's how much we would end with at the bottom, right? I want to look at this idea right here. If we start this water tornado and it starts leaving the top, what would that tell you? We have change happening there, right? Do you think it would be constant or non-constant, the way it's leaving?
Constant.
Constant. So we're going to have a constant rate of change here. Would it be a positive or a negative rate of change? Negative. Why negative? It's decreasing. The water's leaving. It's draining out of the top. So this would be a constant negative rate of change. What's another word for rate of change?
Slow.
Slope. So what about on the bottom? We have that liquid is entering the bottom. What could you tell me about that? I'm sorry, one more time.
We could flip the bottle and see if it's gonna be the same way as the top.
You could flip it over, and it would kind of mimic what was on top before. We said that the water is entering the bottom, right? So, would it be changing over time?
No. Wait.
The amount of liquid in the bottle, would it be changing over time? Getting bigger or getting smaller? So what would that mean about my rate of change?
Positive.
It's positive. I have more and more liquid coming in. The water level is going up, so I'm going to have a positive rate of change. Or slope. One more thing I want to look at on this. I'm not going to go back to the video and time it, but let's just pretend that I watched that video and I was able to measure how much water left the top, and I timed it on my watch, and let's just pretend that I watched it drop 1 centimeter in 1 second. So from the top, that water level drops 1 centimeter in 1 second. What would that tell you about the bottom? That it's gaining what? That it's gaining 1 centimeter of water every second. So the rates, the rates are constant, but between the top and the bottom, they're going to be the same. It's going to be the same constant rate, just one has a negative because it's leaving, and the other has a positive because it's gaining. Rates are the same between top and bottom. Just one negative and one positive. However fast it's leaving the top, that's how fast it would be entering the bottom, because it's a closed system here. And I apologize for my really messy handwriting here. Okay. I want to look at this graph down here at the bottom of the page. This graph was made about one of these water tornadoes. And you're going to have to just put up with my really, really horrible representation of the two soda bottles together. It's a lot easier to copy and paste this shape than two soda bottles. What do you notice is happening based on the graph that we made?
Decreasing.
It's decreasing. So is this graph telling me about the top or the bottom?
Top.
The top. Why?
Because it's going down.
It's decreasing. It's going down. This is a graph
So fancy.
of the top. Because it is decreasing. My handwriting is just horrible today. I'm really sorry, guys.
Mine is too.
If you can't read any of the words that I wrote, please let me know. Those of you that don't know me because you haven't had me before, my handwriting is normally way better than this, and I'm super embarrassed right now. I don't know what my problem is. Is there anything else that you could tell me about the top part of this water tornado?
Well, it starts at 5 centimeters.
Starts with 5 centimeters of water in it.
Then it goes down, it's at 5%.
Starts at 5 centimeters. So if I wanted to draw a graph for my starting amount, I could do it like this, right? And then the water from there is going down into the bottom. What is the rate for how fast it's going down into the bottom? 1 centimeter per second. Water is moving at 1 centimeter per second. With this information, could we write an equation for this? So I would have y equals, I want to write this in slope-intercept form, y equals mx plus b. What does m mean?
Slow.
Slope, which is the same thing as what?
Rate of
Rate of change. What is the rate of change here? Be careful. -1. Why -1? Because it's decreasing, it's leaving. So -1x plus 5. Yes. Mm-hmm.
Wouldn't the x be also the rate of change or just
The -1 is the rate of change. The x, that's a really great point because I was actually getting ready to talk about those variables there. That was my next point, so you like led right into it. It's almost like I planted you there. That x is our independent variable. Look down at the x-axis of this graph. What are we measuring along the x-axis of the graph? Time. So I'd have -1 t for time, right? Plus 5, and that would tell me what's on my y-axis. But what is on my y-axis? The height. So I'm going to use h. So -1 centimeter each, t means time, so each second. What this means is that I can figure out, if I know what the time is, I can use that information, sorry guys, if I know what the time is, I can use that information to figure out how much it's gone down by from that starting amount. And I can then figure out what the height in the top is without even looking at it. I would know. Does that make sense? So like if I had a huge water tornado, I'm thinking like, you know, sometimes in science classrooms they'll have something that's like just enormous for demonstration purposes. If they had this huge water tornado and you're like, it goes for a good 10 minutes, you could make predictions about where that water level is without even having to watch it anymore. And then you could go back and check your hypothesis and see if you're correct. Right. Flip the page over for me. What is happening as you move from picture 1 to picture 6?
It's decreasing.
It's just there's no points on the graph.
Yeah, at first there's no points on the graph, so this must be telling me what?
It's
What it starts with,
What it starts with. What do you notice about the starting position of this?
that there's already water at the bottom.
There's how much?
I don't know, I can't see.
not.
There's 1. Yeah, it's in between the 0 and the 2.
It's a little like a nut.
So right down here, it's in your book too, dear.
Oh.
Bottom starts with 1 centimeter. Top starts with how much?
4, 5, somewhere between.
5. How do you know it's 5 and not 4? Yeah, it's like above the 4 but below the 6. So right here, top starts with 5. Water's decreasing over time. So it is a top graph. What's the rate?
Of what? Oh, wait.
Yeah. At a rate of -1 centimeter
Where do you get -1 from?
each second. Good question. Where did I get -1 from? Yeah. So when I'm looking at this graph, here's where we started. It went down 1 centimeter when we moved to the right 1 second. Down 1, right 1. And when we're talking about slope, when I'm talking about rate of change, when I'm looking at a graph, it's what over what? Rise over run. So if I'm going down, that'd be a negative, right? -1 over 1. Whenever I move to the right on my run, that's a positive. If you ever find yourself counting the other way, you're counting to the left, that would mean the bottom is a negative, okay? So when you do rise over run, it doesn't matter where you start and where you go to from there. Just remember, if you're going down, it's negative. If you go up, it's positive. If you go right, it's positive. If you go left, it's negative. Okay. So top starts with 5 centimeters, bottom starts with 1 centimeter. The water is decreasing over time, so that means it has to be a top graph. Where does it end at? So I'm looking down at picture 6.
Oh.
Looking down here.
Yeah.
What does that mean then? 5 what?
Centimeters?
5 seconds for what to be true? Yes. Takes 5 seconds for the top to drain completely. No water left, took 5 seconds. How much water is on the bottom?
5. Wait, 6?
6. Why?
Because the centimeter stayed already started now.
6 centimeters total in the bottom. Do you guys remember back at the beginning of this when Sydney said the total amount of water stays the same? Because it's a closed system, there's no holes for it to drain out of. So if my starting position, if I was impatient, like my 5-year-old daughter, and she turned this water tornado before the top was completely done draining, so there was still a little bit down on the bottom at the beginning, how much water is in this closed system here? 6 centimeters total. I can think of this as 6 centimeters of water total in this closed system. So if I got really impatient, think of me as my 5-year-old, super impulsive, very impatient. I'm watching this water tornado go. My mom started it for me, and I'm like, nope, I want to do it. Give it to me. And I take it, and I turn it over when there's still 2 centimeters here. So I turn it over. That 2 centimeters is down on the bottom. How much water am I starting with at the top? 4. There's 2 at the bottom, so there would have to be 4 up here. Why?
Because equals 6.
The whole thing equals 6. Does that make sense? Okay. As we're looking at this activity moving forward, I want you guys to keep that in mind, because everything I give you from here, this is the case. There's 6 centimeters of water total in this closed system. So if I start with 3 on the bottom, there's got to be 3 on the top. If I only start with 1 on the top, there's going to be 5 on the bottom. The water total is always going to add up to 6. All right, let's go to the bottom of this page. I promise we'll get to something more interesting here in a minute, but we got to make sure that we understand the setup, or the activity makes no sense. I want to make a graph that represents what? bottom. I want a graph that represents the bottom now. So what's our starting position here? Yeah. Yep, starts with 1 centimeter. So how do I graph that then?
Put one line, dang, hold on.
Start at one, put a point at.
Yep, put a point at 1 on my y-axis. That's my first dot. This is 1 second later, and we're at what? 2 centimeters. So 1 second later, we're going to be at 2 centimeters. Then I have 2 seconds.
4, 3.
We're at 3 because it's in between the 2 and the 4 right here. 3 centimeters.
4.
At 3 seconds, we're at 4 centimeters.
6. Wait a minute.
They skipped a step, didn't they?
Yeah.
How many seconds would this be?
1.
We've been counting by ones up to now, but it's been it's been gaining how much? So this would have to be 5 seconds, right?
Yeah.
I must have looked away for a little bit. We've got 6 centimeters of water. I looked away and missed some data. Because we know it makes a straight line. Whenever you draw graphs for me, guys, super important, connect your dots. Connect your dots. It is not considered a finished graph until you connect your dots. Question.
Answer.
Most of the time when we make graphs of lines, we stick something on the ends of them.
That means the arrows.
We put arrows on the ends of them. Should I put arrows on this graph?
No.
Why not?
Because all you have is 6 and
Yeah, like at 5 seconds, it's done, and I don't get another centimeter of water. Why wouldn't I have an arrow going the other way?
Your green DP.
Yeah, I can't have negative time, right? So I can't move to the left because I can't have negative time. I can't keep moving to the right because I can't get more water in this system. This is going to have just dots on the ends of it. All right. Flip the page for me. I'm going to introduce what your activity is, and then we're going to pass it out. I'm going to put you guys into some groups. We're going to have different graphs that represent what? Look up at the top. The flow of liquid. Yeah. Either out of the top or into the bottom of the container. What do I want to know? Keep reading. What do I want to know? It says use this information.
Which one is the top and which one?
Top and bottom of the same container. Ooh. I want to figure out which ones go together. So which top graph matches which bottom graph? What should I be looking for to figure that out? What would have to be true for them to be the same container? Yeah, same container means the rates are the same, but what?
But the
When you say different ways, what do you mean?
One can go down and one can go up.
Yes, one goes down, one goes up, but one goes down, so that would be negative. That would be our top. One goes up, positive. That would be the bottom. What else can I use to figure out which ones go together? Rates is really important. What else? What did we say about this whole system? Total amount of liquid is what? Stays 6. Total amount of liquid in the system always adds to 6. So if I look at this graph right here, card G5, is this one a top or a bottom?
Bottom.
This one right here?
Top.
How do you know it's a top?
Has a negative slope.
Negative slope, it's decreasing. So this one would have to be a top. Because the water's going down. How much did it start with?
6.
Started with 6. So if I was going to find the graph that matched with this, how much would the bottom be starting with? Bottom would have to start with 0 because it has to always add to what? Always has to add to 6. What is our rate here? How fast is it losing water?
30 seconds.
It took 3 seconds to lose how much? 6 centimeters. So I would go down 6, right 3. Can I reduce that at all? -2 when I divide that on my calculator. Here's my rate. So if I was looking for the bottom one that matched this card right here, I would be looking for a starting amount of what again? 0. What would I be looking for on the rate? +2, because if it's leaving at 2 centimeters per second on the top, it's rising by 2 centimeters per second at the bottom. Do you think any of these 3 graphs would be the bottom that goes with this one? No, why not? None of them start at 0, right? Okay. Do you see 2 that look like they might go together?
The top above.
This one? Okay. Is this one up here a top prism or a bottom prism?
Top.
Top. How do you know?
It's decreasing.
It's decreasing. Water's leaving. How much water does it start with?
4.0.
Yeah, 4.0 or 4. They just got all fancy with their measuring. I'm thinking about like a science class where you got lots of different people recording data. Everybody records it slightly differently. What would the rate be here?
4.0.
-4, because it goes down 4 and right 1, so -4 over 1, so -4. Which one of the other 2 graphs would that mean it matches with?
Wait, what did you say?
We've got 2 other graphs. I want to figure out, this is a top. I want to figure out which of these two would be the bottom part of the same prism. Because here's what I've got so far. You guys are going to have to put up with my super bad artwork. Oh, that's hideous. We've got 4 centimeters here. Bottom right one. How come? Yeah. Even though they didn't mark all the little lines there, I know it can't go with this one because why? That already has 4, and altogether it has to add to 6. I know the bottom has to start with 2. So I'm pretty sure that it matches with this one because this looks like 2 right here. How could I be sure of it?
And the rate of change.
The rate of change. Okay, so that's 2. We're assuming that it's 2. It's going up, right? This is a bottom because it is gaining water. It goes up how much? Up 4. How long did it take to do that? 1 second. So the rate is 4/1, or 4. So I know the ones that go together would be G2 and G6. Do you guys understand how we did that? Okay, because I'm going to hand you a set of cards, and this is what you're going to be doing with them. We've only got about 5 minutes, so honestly, I'm going to give them to you right now to start familiarizing yourself with them. And then when I see you guys again on Tuesday, that's when we'll get on in our partner groups, and you guys will work on these. Because after you get the tops and the bottoms matched together, then we're going to match it with the right picture that's going to be a whole lot prettier drawn than mine. Okay? So I'm going to pass everybody out a set of these graph cards. Jot down ones that you're like, I'm pretty sure these go together. Jot them down in your book. So on Tuesday, you can kind of start from there. Okay?